Hello everyone, I'm Farid Al Saad, a PhD candidate in UIUC. In this presentation, I will talk about our paper, Unsupervised Approach for Modeling Content Structures of MOOCs. The motivation behind this work is according to Class Central, by the end of 2019, there are over than 13,000 MOOCs offered by 900 universities worldwide. Having this amount of courses, there are many courses that teach the same subjects. So for example, as you can see from the picture in Coursera, one of the leading MOOC platforms, if you search for machine learning courses, you will find many courses offered by different universities. So understanding similarities and differences across such similar courses can be very challenging for learners. So with such an increase in the amount of courses with similar content, the problem we are interested in is how these similar courses are related to each other. What are the common concepts taught by the majority of these courses? Is there a common path shared by these courses? What about other alternative learning paths? So, in general, we are interested in capturing the content structure of similar MOOCs in a way that can detect the similarities and variations in the learning paths. Previous work captured prerequisite relationships between courses, lectures, and concepts, but prerequisite relationships cannot detect the variation in the learning path between similar MOOCs. So our approach to model the content structure of similar courses is to use a precedence graph. But what is the precedence graph? It is a directed weighted graph where nodes are clusters of similar lectures across courses. So for example, node 1 is a cluster of lectures like file, processing file, reading a file. And each node is characterized by some key terms or key concept to represent the content of lecture belong to each node. So for example, node 1 has open file, file object, file writing. All these are key concepts that represent the content of the cluster. And nodes are linked to each other by a directed edge where the direction determines the precedence relationship between nodes. And also edges have weights to reflect the strength of the precedence relationship or how common this relation is. So in this picture, we present the main idea of building the precedence graph. We represent each course as a sequence of lectures. First, we cluster similar lectures from different courses, as you can see in B. And then we use the sequence relation between lectures to capture the precedence relation between clusters, as you can see in C. So, our approach for clustering is based on constraint-based clustering algorithm called pairwise constraint k-mean, PCK-mean. And we use PCK-mean to guide the clustering process to cluster lectures across courses to capture the similarities between courses. In this paper, we propose a method that uses course content to generate the pairwise constraint in order to restrict the clustering process. Before digging deep into our approach, let's explain the idea through an example. So given 4 courses that explain unsupervised clustering algorithm, our goal is to build the precedence graph that capture the common and alternative learning paths in these courses. So our goal is to build this precedence graph where nodes are clusters of lectures and nodes linked to each other by precedence relationship. And from the graph, we can see that we can extract common path where, for example, the student can start with introduction, going to k-means, then agglomerative clustering, DB scan, after that, data compression, and finally, PCA algorithm. Having this graph can help a student to customize their learning paths. It also helps instructors to identify missing topics in their MOOCs or find a better ordering of the topic. And as a result, incorporate this new knowledge in their next course offerings. So before explaining our method, we need to mention how the content of MOOCs is represented. So each course is a sequence of lectures, and each lecture has a title and a transcript. In the paper, we represent lectures using two different representations. First, use simple bag of word representation where titles are represented using term frequency, while transcripts are represented using TF-IDF weighting. We also examine other representations that capture the semantic similarity between text by using unsupervised smooth inverse frequency USF, called USF, which use pre-trained word embedding to represent text taking into consideration the frequency of words in the text. So in this paper, we use GLOVE pre-trained word embeddings. To build the presidency graph, we first need to cluster lectures based on their similarity into cluster to construct the nodes of the graph. Then we link the cluster to determine the precedence relationship. And finally, we represent each cluster by key terms to explain the content of each cluster. So since our goal is to capture the similarities across courses, we want to restrict the clustering process to cluster lectures across courses by enforcing some constraint. Therefore, we exploit BC K-mean. So basic K-mean is just a variation of the standard K-mean algorithms as it incorporates pairwise constraint along with the distance between points to guide the clustering process. Basically, there are two types of constraints, must-link constraint and cannot-link constraint. The basic idea of BC K-mean is to group lectures into cluster by minimizing the penalty cost of violating each constraint, as well as minimizing the sum of the square distance between the points and the centroid of the cluster they belong to. So the question is, how can we select examples of lecture pairs for the list of must-link and cannot-link constraints? The idea of must-link constraint is that we want to feed the algorithm with examples of lecture pairs that need to be clustered together. So we use the cosine similarity to calculate the similarity score between lectures and then choose pairs that have similarity scores exceed some predefined threshold. Since we want to capture the similarity between courses, we choose lecture pairs from different courses. However, some adjacent lectures within the same course are very similar to each other and need to be grouped together. So for example, if we have a lecture called K-mean algorithm and then the next lecture is initialization of K-mean clustering, in this case we need to group these two lectures into the same cluster because they have similar content. And to capture the similarity, we assume that lectures are similar when they have similar transcript or when they have similar titles. On the other hand, cannot-link constraints are used to feed the algorithm with example of lecture pairs that shouldn't be grouped together into the same cluster. So the idea is that we want to use lecture pairs from the same course as example to cannot-link constraint. Why? Because we want to force the clustering algorithm to cluster lectures across courses to capture the similarities between courses. To do that, we look for the topic shift between adjacent lectures. So for example, if we have LJ and LJ plus 1, and when the similarity score between LJ and LJ plus 1 less than some predefined threshold, in this case, we can say that there is a topic shift between LJ and LJ plus 1. And as a result, we can pair LJ with the lecture LJ plus 1 and all the lecture that comes after it, and these are considered examples of cannot-link constraints. After finding the clusters or nodes of the graph, we need to link the scattered cluster by using the precedence relations between adjacent lectures. And we accumulate the frequency of courses to capture the edge weight or how common the relation is. The final step in constructing the precedency graph is to label each node. To do that, we accumulate the TF-IDF vector representations of lecture transcript and also accumulate the term frequency vectors of lecture titles of each cluster and then use the top K terms to label the nodes. For the evaluation, we want to evaluate the performance of our approach for clustering similar lectures using BC-K-mean algorithm with the proposed pairwise constraint compared with the standard K-mean. To do that, we use 6 models from 5 real machine learning and data mining courses from Coursera. And to build the ground truth, we asked 4 annotators, or 4 experts actually, to group similar lectures into cluster, and we took the majority votes. To measure the level of agreements between annotators, we use FLIS-Kappa, and the Kappa score was 0.65, which indicates substantial agreements between the annotators. So for the evaluation, we ran each algorithm 20 times and recorded the average and max score of adjacent mutual information, AMI, and Folkes-Mauer's index, FMI. We can see from the table that BC k-means outperform k-means in both representations, in TF-IDF and bag-of-word representation, and also in USEF representation. And when we compare the performance of BC k-mean, we found that TF-IDF and bag-of-word representation outperform the USEF representation, and all the results are statistically significant. We also studied the effect of using the lecture titles and transcript when generating the must-link constraint to study the effect of or how lecture title and transcript can be used to capture the similarity between lectures. We compared the performance of the BC-K-mean algorithm using only must-link constraint from titles to the performance of the same algorithm using only must-link constraint from transcript. We used TF-IDF and bag-of-word representation as it achieves the highest performance. From the table, we can see that using both lecture titles and transcript to produce the must-link constraint achieves the highest performance. We conclude that titles and transcript representation are important for capturing the similarity between lectures. We also noticed that removing must-link tuple of lecture transcript reduced the clustering performance more than removing title tuple, and this is expected as lecture transcript contain more keyword than titles. However, using only titles to generate the must-link constraint tuple achieves comparable result, which also indicate the importance of using titles to capture lecture similarities. We use also our approach to create the presidency graph that represent the 6 models in our data set, and we extracted several learning paths example from the presidency graph. So for example, you can see in the picture that the first path we extracted, we call it follow the crowd. This path actually is a common path and it is shared by many models in our data set, and students who follow this path would have a good overview of the topic as it explained the common concept in the field. The second example is a path that we call it the expert learning path. It is also one of the longest learning paths that span over 7 nodes. This long path is more comprehensive than the common path and explore more clustering algorithm, and students who are interested in gaining comprehensive knowledge or becoming expert about the clustering algorithm will find this path very rewarding. Finally, the third example we extracted is a subgraph that we call it give me some options. This subgraph has similar alternative learning paths, and students can customize their learning path by choosing the learning path that fits their needs. Also, the subgraph gives students a comprehensive overview of how concepts are connected among several courses. So there are some limitations in our study. First, we haven't addressed the problem of cycles in the presidency graph, and we plan to address this problem in the future work. Second, we evaluated our approach only on one domain using machine learning and basically clustering algorithm. In the future, we are planning to evaluate our method on other domain, and actually we apply it now on Python courses, and the results were promising. So to conclude our work in this paper, we proposed the idea of the presidency graph, and we developed an approach based on BC-K-mean clustering to build the presidency graph. And we propose a method to generate the must-link constraint and cannot-link constraint to guide the clustering process. We also generate the presidency graph from of our data set and extracted some learning path examples. We consider the presidency graph as an initial block for building many applications that support personalized learning. So that's all what I have, and thank you.